I think we have an interesting meeting on floods, and we brought together interesting people because we combine people from those who invest, the World Bank, the friendly researchers from the research institutes, and those who make money from their support on the governments and the other consultants. I was actually it was planned that I would chair this meeting with Rosage Guale from the Environmental Lab on hydroelectricity in Bahora Bassa, but he couldn't come, unfortunately. And from my point of view, I'm from Deltares, I'm Jaap Kwadijk, and I can think I'm from the Netherlands, and in the Netherlands, floodings is the topic, right? I mean, there's no question about it, and I can assure you that lots of our annual turnover of my research institute is dedicated to flood research. What we will show this afternoon is actually, I want to see a bit more optimistic about, there is a lot there already to do all kind of assessments. What we will see, first of all, Hessel and Semis will present an overview of all the requirements on different scales for flood risk modeling. Then the next speaker, Suzanne Stanton, Geddes from the World Bank, she will provide the information that is needed on the real scale. That's where it happens, in the urban flooding. Then Hamish Hall will provide us with some information on rapid flood modeling, which is an extremely handy tool to do the thing. And in the end, Mr. Brandon Youngman from the Institute of Environmental Sciences of Free University, he will provide you with an example what can be done with the global flood data for Africa. I would like to ask you, rather than to think, oh, what a great research is this, to listen to the people and really listen on a way that you can identify those things that are really interesting to use, because that's what we are doing it for in the end. And please give comments if you think that there are things that you cannot use at all. I mean, don't hesitate to tell us that. That's what we learn from it. All right, so I would like to ask Hessel Winsemus to start with his presentation.
Okay, ladies and gentlemen, thanks very much for attending this session. And Jaap, thanks very much for the introduction. Indeed, what I will try to show is a bit progressively what I showed yesterday briefly during the Ignite. There's different scales of information needs, and hopefully there are also different scales at which these information needs can be provided. Yeah, it's a bit provocative. Size matters. This goes a bit towards the end of my presentation today. I will show that it is really important to realize that when you really go to a very detailed and small scale risk assessments, then you really have to take into account that the resolution at which you do this becomes very, very important. Now I hope that, no, this is not the right one, of course. I have to move forward somehow. Can I do it like this? Yes. So, which information is useful at which spatial scale? That's what I'll start with. And yeah, and then do we have something available to establish these risk estimates? And I will also look forward towards the remainder of the presentations, because I'm not the only one who's talking about this, of course, today. And then does the size matter in our calculations, yes or no? So, a little bit more extensive with respect to what I showed yesterday is, well, if we look at the global scale, what sort of questions arise then? And this is not an exhaustive list, not at all, but just a few examples of what type of information you could think of. So, which country is more exposed? A bit into the GAR session of the last hours, which probably many of you saw. Overview of where is it safe to invest? Where can I do my investment without having to worry about floods? And this picture, picture of Al Gore, gives you an idea of what level of information you then get if you make such an assessment at global scale. It gives you an idea. This country here, this is our country, the Netherlands. It could be exposed to floods. If nobody did anything about it, it's exposed to floods. And that's sort of the level of information that you can expect from global scale calculations. Another question could be how to distribute funding for adaptation, where to really focus on adaptation investments. Now, if you go to a regional scale, and for example here, Thailand, for instance, then the questions become different, and information needs as well. How high should my premium be? How high should I set the premium for insurance against floods? How much cover should I buy this year for reinsurance? What should my solvency be this year? And multinationals, okay, I have some assets on the ground, and should I worry about demand supply chains? IBM had a huge problem here in Thailand because they couldn't manufacture their hard disks anymore. So they needed to go to another manufacturer for hard disks to make their computers complete. And this is just an example of the level of detail that you would require probably on this regional scale. In blue you see the flood extent, and in red you can see where the assets approximately should be according to a land use map. And then, where and how much money should we invest in flood protection? Where is the trade-off in letting a flood happen and accept that there's some damage and you can deal with it, or you have some insurance against it, or where should you go towards really infrastructural measures to prevent these floods? And on an even more local scale, and really at the asset scale, and this is, I also showed this yesterday, then at the asset scale you could focus on, is this specific asset under threat, but also if something happens, can I still evacuate, yes or no? And this requires really a high detail of information. And then this example, where and how much money should be invested in flood protection of specific insured objects. And should I protect it, or should I buy insurance? That sort of questions arise then. Require a completely different detail of information. So what do we have available at these scales to provide this information required to answer these questions? And I think in the discussion it would be very useful to have some ideas of whether this type of assessment is useful to answer these questions, yes or no. Well, at a large scale, we have methods in which we use global data and global models of hydrology and rough estimates of hydraulics to answer these global questions. And we already have some infrastructure available to apply these global hydrological models for such global assessments. And to progress the risk, we really use global available information on elevation, for instance, which areas are close vertically with respect to the river and which areas are high. And things like OpenStreetMaps to have an idea where are the largest assets located. And Mr. Jongman will tell much more about this in a later in the one of the next talks. But there's no system information included whatsoever. So whether there are dikes or control to flows or reservoirs available, it's not there on this scale. You don't have this. You cannot include this information very easily. At the regional scale, then you can start to look at these system things, and you can also think about, okay, in this region of interest, what becomes important then is to have an idea what are really the most stressful events. On the global scale, you focus more on what is the average damage, what is the average affected people, but on this scale, it's really what really matters for the assets in my region. And then this Fukushima example in Japan is a very clear example of that, I think, where what is a stressful event? It's not that an earthquake occurs or a tsunami or a flood wave occurs. It's when they occur at both at the same time. Then you get this domino effect, and then you really have a problem. And then you could identify what is the probability of that occurring. And in the Netherlands, we also have some example like this. So this is one of the famous storm surge barriers in the Netherlands. And it's meant actually to prevent that a storm surge goes into the country and inflicts a lot of damage there. But what you should be interested about is when does it fail? And it fails actually not just when you go over the design criteria, but also when something in addition to that happens. If you have, for instance, a high storm surge on this side, and at the same time you have high flows from this side. Because then when this storm surge barrier closes, then yeah, the whole area will fill up from the inside basically, and you may have a problem. And in fact, in National Geographic, they once showed a program where you can see that if this really occurs, then this whole thing could actually flush away. So, and these are the stressful events that you should then look at. Another stressful event is failures. What if one thing fails? What is then the probability that another thing fails? And in this, this is a movie which I will show. You can actually see what happens if there's a dike breach over here. Then you will see that this water will progressively flow into the country, and it will hit another levee, and then this levee, because this levee already broke here, it will also break over there. That wouldn't have happened if this levee breach wouldn't have occurred over here. And you can see that very nicely happening here. That's the next breach, and then there's another levee. It takes a while, and then the stress becomes so high that also this levee, it will collapse as well. And this levee would have still been there if this wouldn't have occurred. So domino effects of failures become important if you focus on regional scale risk. Now then towards the local scale, then does size matter? That's a bit the question I try to answer here. Well, there are nowadays solutions available, software solutions, and you have a leaflet on your chair available. It's called 3DI, which actually enables us, if the movie works. Apparently it doesn't, so that's okay. Something happened, but see this. Yeah, here you can see it. This is a breach along the Dutch coast, and we can actually estimate on very high resolution where this water will flow to and what the water depths become if this happens. And then you would say, okay, well, why don't you do this on a lower resolution, on 100 by 100 meters? Well, you could do that, but if we go to the next slide, you can see what the difference is between a low resolution computation with exactly the same boundary conditions and a high resolution computation. You can see that on the high resolution, not only you get a lot more detail, but you really get a different answer. So if you want to know which areas, particularly on this small scale, are under threat, it's really essential that you go for a high resolution computation. And you can see, for instance, that here there's apparently no flood hazard whatsoever, while on the high resolution there is flood hazard. And here you see another example. Here on the high resolution there is no hazard here. On the low resolution there is hazard here. And that has to do with the very small detailed topography that occurs in reality, and that you see displayed here, which is sort of smoothed out if you go to a lower resolution. So you don't see that small scale topography, small obstacles and small drainages. You just don't see that on the low resolution. And for risk estimation, that's really important. And if you go to the information that you eventually want out of this, is this asset under threat, yes or no? Well, there's a whole bunch of assets under this picture, and so, yeah, where exactly does the risk occur? You cannot see that. And you see that there's all these red blocks indicate that there's a lot of risk, but where exactly it occurs, that is the information that you're interested in, you actually cannot see. If you go to a high resolution with this new software, you get much more accurate risk estimates in space, so you can more accurately design how high your levees should be to reach the correct safety level, and also much better establish how much insurance premium you actually require to eventually even out the risk. And now you can really see that this particular house here, this row of houses, that's the row of houses that's under risk. But this row of houses here, with the light red color, the risk is much lower. So it really matters that you, at which spatial scale you estimate such risks, if you go to the resolution where it really matters, the actual damage. So conclusions, well, what we try to do and what we also try to show in this session as a whole is we try to provide flood risk estimation at all spatial scales. Large scale based on freely globally available data and hydrological models. We make it applicable that's already applicable everywhere, I would say. On regional scale, we try to take into account as much as possible this system behavior. And we had a nice presentation from Mr. Razak Gouali for this, but unfortunately he's not here today. And local scale, then really size starts to matter. And we already have software available to utilize high resolution data. The only question that remains is, can we apply this everywhere, this high resolution solution? That's a bit of the question. And well, luckily in a few years we will have this global 12-meter elevation model available from a new elevation mission. And that actually provides us what we need to make these computations. Global coverage and unprecedented accuracy all over the world. So I would say yes, we can. But I'd like to see your comments, of course, after all the after all the remainder of the talks. Thanks very much.
Thanks, Hessel. I think there's room for questions. We can discuss general things later on, but if there are questions for Hessel's talk, please don't hesitate. I have a question. Oh.
Yeah. The TAN digital elevation model, is that going to be freely available, going on the themes of earlier?
Yeah, I think so. I think it's going to be freely available. What I heard, not directly, but I heard that in 2013 the first samples of this elevation model will become available for study anyway. It's probably not available for the whole globe then, but at least to have first ideas of what you can do with these data. Yeah.
Yes, you show 12 times 12 meter horizontal resolution.
Yes.
I'm very interested, of course, in the vertical resolution, but simulations.
Yeah, okay, perhaps repeat it in the microphone.
Yes, the question was, although the horizontal resolution is 12 to 12 meters, which sounds very, very accurate, in flooding vertical resolution is very essential. That was the question. How good is it?
Yeah, so the highest resolution elevation model for the globe is now the Shuttle Radar Topography mission, and that has I think a relative accuracy of about 10 or 15 meters, I believe. And this mission, I read some of the specifications, and the relative accuracy should be about 1 meter, so it's a lot higher than SRTM. And the absolute accuracy, so if you look at really absolute in elevations with respect to a certain level, then I think it's about 10 meters. But I think the relative accuracy, in particular for hydraulic modeling, is the most important thing, of course. So about 1 meter, that's what I read about it. But I think we have to find out as soon as we have the first samples, of course. Yeah. There's a question over there.
Yeah, that's a related question. Okay, just a related question. I guess it is a little bit oversimplifying the detailed flood propagation which you showed in your map. Like you're saying 10 centimeter water level differences. When we talk about 1 meter even contours or DM, you can never get this 10 centimeter water depth in flooded areas like in flat countries. So I think this oversimplification of large scale or small scale flooding using such a global data, I think is kind of too optimistic. So we might get false information. I think there is no option to have local elevation topo data if you really want to do detailed flood risk mapping.
Yeah, I think, well, it's a bit the question, do you want to do nothing or do you want to do as much as what is possible? And I think that as soon as we have this 12 by 12 meter elevation model, we should at least try to find out how much can we get from it. And at least we already have numerical algorithms in place to actually test this and to try this out. But I fully agree with you, and we have to make sure that we know how much we can expect from it, and what also validate how accurate can you be with this global with this globally based satellite-based elevation models. And yeah, and I would also agree with you, if you have locally made elevation models available, they're probably always more accurate. Yeah.
Thanks for the presentation. 2 quick questions. One, can you give a scale of cost for the 3 different options? And secondly, like it's interesting that you precise what kind of difference you have when you get when you diminish the uncertainty on the resolution. But without going into the details, like we know that there are in flood modeling there are like a number of little technical choices, a lot of uncertainty that do not relate specifically to the topography. for a given resolution, what about the uncertainty over the other parameters? Thank you.
Sorry, the uncertainty of which parameters were you referring to in the last question?
Well, like it could be like, how do you cut the grid? Like all the little, like the equation you use for propagation, diffusion, the model, rugosity model. I mean, we know that in hydraulics and hydrology you have the rain discharge flow transformation. Well, there are thousands of modeling choices that relate either to hydrology, hydraulics, or to computer science. Plenty of choices to be made. The point is to say, does it really pay to go on a better resolution if you maintain a very large uncertainty on the other? Well, I think you got the question. Thank you.
Yeah, I think the benefit if you go to this very high resolution, I think then the amount of assumptions that you have to make becomes less. For just a simple example, if you would model on a very coarse resolution and you don't take into account that in reality there's a lot of variability in elevation, actually that has a lot of implications on your roughness. Which roughness value are you going to use for this modeling? So you have to sort of parameterize the fact that you don't have information about the smaller scale variability in elevation, and you do that usually by tuning your roughness parameter. If you go to a very small, very high resolution, then that roughness is in your elevation data, so you don't have to make these assumptions. I think that is one of the strengths of going towards a higher resolution solution, I would say, that the amount of assumptions that you have to make becomes less. It becomes more physically based, the modeling approach that you follow. So. You mean the land cover and then related to... it's a bit of a detailed question, but the land cover related to the roughness also, or is that what you mean? Or?
I want.
The land cover will relate to you what is on the ground. Your DM is a surface, a ground surface. So how much of land cover exists above the ground surface, and how high is it?
Okay. Yes. I see what you mean. Yeah, and that's okay. That's true. You have. There's of course some processing required to make these elevation models more suited.
I think that is where the aspect of 3D GIS comes in.
I consider it a very interesting discussion now, but I would like to, because this is very detailed, and I'm happy to discuss it separately.
Okay.
I would like, actually, I would thank the people who asked questions, but I would like to continue, because otherwise it becomes very, very late. Yeah, okay.
Thanks.
Hessel,
right.
Thanks very much. I want to invite the next speaker, Ms. Susanna Stanton-Geddes from the World Bank, and she will tell us something about urban flooding. And I think that's high on the agenda, particularly after what happened in Bangkok. Susanna.
Thank you. So Hessel started this session with talking about scales, global, national, regional. I'll be talking about one of these scales, cities in particular, and I won't be talking about models, sorry to disappoint you, but I'll be talking about an approach that policymakers can make to make their cities more flood resilient, meaning their infrastructure, their communities, their institutional and their financial arrangements. Floods can have truly devastating impacts on the urban dwellers in developed and developing countries alike, and we've seen it in the past year, and Thailand has been mentioned as one of the examples. The key reason for World Bank's engagement in this area is that urban flooding poses a serious developmental challenge for the fast-growing low and middle-income countries, especially their poor and vulnerable groups. Now, this conference is about understanding risk, so I'd like to add a little bit to our understanding by Firstly, briefly just talking about some of the recent trends that we're seeing in urban flooding. And secondly, explaining what is meant by this integrated flood risk management. And thirdly, give you a few examples from the East Asia and Pacific region. So the trend we are seeing in the past 20 years in particular is that floods have become the single most frequent disaster occurring. And the larger graph on my right shows this, this trend. The average annual number of recorded flood events is growing the fastest. It is the gray dotted line. Now, in terms of the impact, while it is encouraging that the immediate loss of life has been globally declining, and we've heard this, Andrew mentioned it in the GAR, referencing the GAR report. However, the number of people affected, the financial, economic, and insured damages have been increasing. So this is truly worrying. Now, the second trend is that we are experiencing the largest wave of urbanization. In 2008, half of the world's population lived in cities, and in 2030, this will be 60%, 2050, 70, and more. But urbanization per se, it's not the main problem. It's when it happens rapidly and in an unplanned fashion. This makes really urban flooding more difficult and more costly to manage. Now, what we also see is that actually the cities that are growing the fastest are the peri-urban, small, middle-sized cities that are already severely challenged in terms of their capacity, ability to invest, and to provide services for its people. So this is very worrying, especially for the poor, vulnerable, informal settlers, etc. So facing these challenges, there are some concrete steps that policymakers can take to make their cities more resilient. Now, integrated flood risk management is a forward-looking approach, and it aims to avoid the mistakes of the past and really turn urbanization, urban growth into a positive force for development. Integrated flood risk management is part of a broader strategy, integrated water resources management, which has been gaining ground at the World Bank, but also with other international organizations. The recently published report, Cities and Flooding, the summary looks like this, and there are a few copies downstairs. Funded by GFDRA and developed in cooperation with WMO and JICA, provides technical guidance and practical tips to policymakers, urban planners on how to implement this. It actually recommends, it makes 12 recommendations or guiding principles, but don't worry, I'm not going to bore you with 12. I'll just focus on 3 that I think are most important in this context. So first of all, we have to recognize that it is impossible to entirely eliminate risk. Cities are complex systems, so that uncertainties and possibility of failure, domino effects, we heard this. In fact, there will be a presentation tomorrow about be prepared for what you can't prepare. And this will, I guess, talk about these sort of large-scale failures in more detail. But what it means really that rather than waiting or trying to find the optimal solution, we really have to take a risk-based approach and look at the various options at the table. Now, the second, I already mentioned that urbanization poses a huge challenge, but at the same time, it is an opportunity to avoid mistakes of the past and have better urban development, so that integrated flood risk management really has to be part of everyday urban planning, urban development. This means relying on all stakeholders, having community engagement, collaboration across sectors and jurisdictions. And the third one, this strategy relies on a kind of the right balance between structural and non-structural measures. And what is this? So structural measures are the measures that keep the water away from the people. They can be hard engineered, all part of ecosystem management. Now, non-structural measures are the ones that keep the people away from the water. And this is really everything and ranging from preparedness, land use planning, early warning systems, as well as risk transfer, risk insurance. For example, an example of where this balance has been achieved is, for example, the German Flood Control Act from 2005, after devastating floods in Germany, which really has a combination of these measures, creating more space for rivers, retaining floods in remote areas, as well as controlling urban development only in specific zones. I mentioned that there's the last part of my presentation focuses on a few examples. Of course, there's a number of projects the World Bank is involved in and pushing through with some of the tools available. We've already heard from previous presentations, risk assessment is one of these tools. Risk-based land use planning, another one. Urban upgrading. Then there is community-led DRM, community participation, open data, risk transfer mechanisms, and specific risk mitigation projects. I will actually focus on two examples that have already been mentioned in the previous session. So if you were there, you will have a little bit of recap. However, I'll highlight different things, so don't worry, there won't be too much repetition. So I mentioned that integrated flood risk management is based on this combination of structural and non-structural measures. But how do you know where are you going to put your money, where to invest? So as you know, Jakarta suffers from recurrent floods, and the 2007 flood was particularly severe. And it really refocused the debate taking place in Jakarta, and more was demanded to do. So the way the National Disaster Management Agency and other partners address this issue is to develop a prototype decision support tool. And the next series of slides will show you how it works. The previous speaker actually showed some of the examples what the tool already entails. For example, data on buildings, people affected. So I'll be actually showing you the people affected by floods in 2007. That will be the first slide. And the second slide will show you the people a scenario of people affected had an investment in a specific infrastructure investment been made prior to the floods. So this one shows you the extent of flooding in 2007, and the hotter colors represent denser areas, and the little table shows you the amount of population affected. Now, you can see with dredging, the areas decline, as well as the numbers, so that had there been dredging implemented, some 33% of population would have been less affected. Now, I would like to highlight really the importance of this tool. It is really critical for an agency like a National Disaster Management Agency to be able to evaluate different investments as well as see it in a visually easy way. Now, this tool really helped the discussion about risk-based approach to floods, as well as facilitated actually negotiations about an ongoing, about a project which then in January was approved, the Urban Flood Mitigation Project, which will actually clean some 68 kilometers of channels and some 60 hectares of 4 retention basins. So it gave a push because there's demand and there was always agency ownership over the tool. There's further development and customization of this tool. Now, this is also a similar example, and some of you might recognize it. Having a tool such as InnoSafe is nice. However, you can't get to such a tool if you don't have the information and the data is not there. So this was really at the heart of the project, the Pacific Catastrophe Risk Assessment and Financing Initiative, which undertook a series of very extensive, detailed risk assessments. I'm not going to go into the details, but data for hazard, exposure, vulnerability was gathered together, collected, so that risk can be calculated. I just want to highlight that, again, having such a tool can have major implications for further development and the sustainable development of these countries. This information, as my colleague mentioned earlier, was shared through an open source system, GeoNode. What does this mean? It means that all the stakeholders have really access to the same information at the same time, and they are able to use it in different projects, whether it is damage assessment, whether it is urban infrastructure projects, or hydromet services. Now, this again spurred the discussion about risk-based approach, and as well as open data, and increased interest in the open data initiative. So those two examples highlighted some of the challenges that countries faced in East Asia, and ways to address these. Integrated flood risk management is a risk-based approach, and it's based on a combination of structural and non-structural measures, and it has to be implemented as part of everyday urban planning and urban development. Now, with this approach, not everything is perfect, of course, and there are many, many challenges and problems remaining. And I would like to reiterate the questions that were posed actually yesterday at the Ignite forum by another speaker. But when we think about implementing this great research, then we have to think about what instruments are missing, what investments are really necessary, how to prioritize them, and then incentives. Why actually isn't this already happening, and what's in the way? So, thank you very much.
Thank you, Susanna. Any questions? And otherwise, I have one. Okay, then I will start. You did these assessments on risk assessments in these areas for the sake of the World Bank.
You mean in the Pacific?
Yes.
In the Pacific, yeah.
Do you now consider that your knowledge on the risk in this area, which is a huge area, is now better than it was before?
Oh,
so much better that you can do, well, we can do now more balanced investments than we could have done, let's say, before the assessment?
Yes, definitely. Actually, it's the largest collection of risk data currently available in the region. And, a lot of people ask, there was a session earlier this morning about financing, risk financing, and there are often people ask, well, why isn't there more risk financing? Why isn't there insurance? And one of the questions is, well, there's no data. If there's no data, they cannot price. There's no trust then in the market to do something like that. So then there's really just the government, the treasury, as the last resort to manage and deal with this. But risk assessments, in this case in the Pacific, are a huge step forward now that this collection is available. I think we can be optimistic that it will lead to greater things.
Thanks. Any questions?
Quick one.
Yeah.
Sure.
I think overall approach, excellent, no problem. My question is on the details you saw, like in the Jakarta flood, you saw that 2,300 people will be affected by 10 centimeter flood. And that's, as engineer, I don't think 10 centimeter is a flood. And you can't get that accuracy by any model, especially talk about tropics. So I think we should be careful when we show the results that less than 30 centimeter in a flat tropical urban country, anywhere, thunder showers, nowhere. So maybe we should be careful in showing results. Don't call 10 centimeters as flood. So maybe if you change that, you might get a different picture on your analysis. Thank you.
Sure. Maybe in response, there's no such thing. Every flood situation is different, and there is no same answer to all of them, and not one tool can help all of them. It really depends on the local needs. Maybe this was what the national agency was interested in, even in the lowest level of flood. This is something that you can, however, change the parameters. You discussed this earlier. For example, the tool allows this to be changed so that in another calculation it would look differently. But the tool has been used in the 2011 and 12 emergency planning, contingency planning exercise, so it was of use so far.
Thanks. Thank you. Just for the time also, I would like to ask the next speaker. Thanks, Susanna. And the next speaker is Mr. Hamish Hall for Royal Haskoning, who will provide us with information on rapid flood modeling, which is an extremely handy tool to have at some times.
There's some seats at the front if people want to come forward while I check my flies are done up. Do you want to come forward? There's seats here. So, good afternoon, ladies and gentlemen. It's a real privilege to be here. I was invited by Hessel to come and talk. I work for a consulting firm of engineers who yesterday became Royal Haskoning DHV. We two Dutch companies combined, and in South Africa, SSI are the operating name. I'd like to thank a couple of my colleagues, Aminal in the UK, who actually did a lot of the numerical modelling. So those difficult questions I can probably pass to him later. And Mariki, who's based in Johannesburg, who gave some common sense tips on what not to talk to you about. I'm not sure I paid full attention, but I'll let you be the judge of that. My career in flood risk management started probably about the age of 3 or 4 by building dams across rivers, as I'm sure many of yours did. I'm lucky enough to be able to continue in that career path of understanding flooding and flood risk. And yeah, it's a subject I'm passionate about, and I became a civil engineer so I could try and keep understanding more about flood risk and do some good. Sticking with the history theme, it's worth noting that there are no experts in flood risk, really. I'm stood up here by invitation, but I'm not an expert. I think all of us are in one way or another, and we can learn a lot from history. And I've put an example of an English church there, which isn't flooded. And that's because people knew not to build in the floodplain. Now, I think Susanna's slide showed it quite well. Up until 20 years ago, that was probably a common sense approach to take. But with increased urbanization, a lack of understanding, people not staying in the same place for very long, we're losing that understanding of where floods and where doesn't, and inappropriate development or sheer necessity to develop in floodplains is beginning to happen. So I will justify my modelling job in a minute. It's also worth stating that you can learn a lot from geography. Wherever I go anywhere, my eyes are open to flood risk. And here's an example in Namibia. The anthill isn't in the floodplain. And I can see the floodplain quite clearly, or the normal flood, just by looking around and seeing where people aren't necessarily living and how the river has carved a channel through the town. When I started my proper professional career 20 years ago, my calculations were done by hand because we didn't have a computer, using the Manning's equation to look at flood risk. Pretty soon, we got some numerical modelling tools, one-dimensional flow modelling, and that's an example of HEC-RAS. Brilliant tool. The reason it's brilliant is because it's free. Anybody can download it. But it did have a visualization problem, and this is sort of a theme that I'm going to keep coming back to, is people need to understand flood risk in order to do something about it. So in the last 5 to 10 years, we've seen development of two-dimensional flow modeling. There's numerous service providers for that. At the moment, a lot of the best ones cost a lot of money, which is a drawback, but I'm sure that will change with conferences like this as we go forward. So here's an example of a model. It's a coastal flooding problem, and it was critical in us planning for and designing a flood defence scheme. It gave depth, damages, but most importantly, it showed people the risk that they had from an extreme event. And it was that understanding of this town that, and their desire, actually their desire to have insurance premiums reduced and to be able to develop, that helped us get a scheme in without too much public opposition. So changing tack slightly, we've still got a lot of flooding. Those are just a few of the floods that my company and I have been involved in looking at in the last 3 years. And so what's going on? I'm better at understanding risk, but actually in the field, those risks aren't well understood. And more importantly, people are powerless to do anything about it during the event, even though the impacts of flooding, as we've talked about, or any risk, are so severe. So what's the problem? So coming to this conference, I had a couple of weeks' notice from Hessel. I'll just grab some water as well. I started to question, with the advent of new technology and increased modelling, why we still got a rising line of the impacts of people. And so I can't answer all those questions, but started with myself. When I start a modelling project, I want good data. I want the best DTM I can get. And I'll persuade clients that they need to fly LiDAR and spend tens of thousands in collecting data. I'll then ask for a couple of rain gauges, some river gauges. I'll do a big statistical analysis on rainfall. These are the budget prices, by the way. We can go higher. The hydraulic modelling, obviously, it requires a lot of time and work, both to get the model running and then to start calibrating it and testing these extreme events. And then finally, it's going to take me 12 months to write the report, of course, because it's a complex job, this flood risk modelling. And this happens time and time again. The flood is a knee-jerk reaction. The investigation takes 12 months. By the time you're out of that 12-month period, the funding's dried up, the river's dried up, and people's appetite to do anything is dried up. So the topic of my conversation is rapid flood modelling. So what I'd like to now move on to is not modelling really big, quick floods, but how to speed this process up. So I decided to choose somewhere where nobody's paying us at the moment, so I can't offend anybody, although there is a gentleman from Namibia Hydrology in the corner who's, I notice, is present. Look at a place I visited in March in northern Namibia that has experienced repeated flooding. Oshakati, and here's a map from 2011. I believe the 2010 flood was just as bad, and it's widespread flooding across a very large area. So I set a challenge to myself and Aminul, my modeler. You have 4 days, or we have 4 days, to work out why does Oshakati flood and what could be done to improve the situation. So I'm going to try and really speed up the process. Oh, and I also said you're not allowed to have any data that you have to pay for. So the first step was to try and find a digital terrain model. And here we use the SRTM shuttle radar topography model, which is freely available. And then some excellent weather records from Namibia Weather and other sites about how much rain they've experienced over the last couple of years. We used the digital terrain model to define a broad-scale catchment. I didn't really care if it was right, because the digital terrain model would show me where my flows went. And my initial plan was to model the big catchment to work out my inflows for the small town of Oshikati. This is where it didn't, I thought I'd give you warts and all, actually. I ran a specific rainfall event from March 2 years ago, and it all started very well. Started defining the catchments up in Angola and defining flow paths, and then it started to fall down. Because I had to choose a large grid size to try and get the model to run in 4 days. And the model was taking a lot longer to run. And it began crashing and becoming unstable until my inflow conditions, sorry, I'm getting a bit technical, really didn't mean anything. So we quietly put that in the bin, and I said I wouldn't tell anyone. And we moved on to a local model. So here we were able to use the full resolution, so the 30-meter DTM from the data that we'd been able to download, and run this model with a dummy inflow, which was based on anecdotal reports when we were there. And you can see the DTM running away there, I mean the flood model running away. Now, that doesn't actually tell me very much, because I went to the site. Let's move on. And I know that right through the middle of our model, there is a large road. Here's a photo I took when I was there. And that road is some 2 meters higher than the ground next to it. And also, there are several bridges, 5 in fact, running beneath that road. So using the power of Google Earth and scaling what I thought to be a 6-foot man, we managed to manipulate the DTM very quickly to create a new model. Put the same inflows in, and you can see the water backing up behind the road. Now, from common sense, that's what I expected to see, so I was quite happy with that output. But with all modeling, you need to do some form of calibration or verification. Instead of 10 grand, I just overlaid the photo and saw that I had some form of correlation or verification against what I've been modeling. So, well, what's the point of all of that? Well, no, how's it go that way? I can start interrogating that model now to look at the differences pre and post putting the road in, and the red colours show the increased flooding when the roads come in, and that's what I expected to see actually, that road was built with without detailed regard for the flooding problem there, and it's actually causing a barrier to flow even with the bridges in. And once we get these big rainfall events, 3 of them happen now, they're causing the water to back up upstream, causing higher elevations upstream of the road and lower downstream. Now, unfortunately, this is the area where the business development is going on at the moment, and that's why it's having more and more of an impact in this town than if the road hadn't been there. Obviously, you need the road to have industry. So moving on then, can the rapid modelling, or could rapid modelling influence decision making? And how do you make the flood situation better? This is a screen grab from a scheme that's planned there at the moment, which is at the Rolls-Royce end, I would have said, of flood defence projects to create a large dike around the town. And honestly, the modelling that I did wouldn't help in that design. You need some detailed modelling to design something like that with confidence and keep the costs low. But if we think about adaptation and resilience, well then that quick modelling that I've done immediately highlights to me that potentially there's opportunity for opening up those bridges to create more flow. Well, that's quite expensive. Or learning from nearby, lowering the road to let more water through to reduce upstream risk. But really, where the benefits to people come from is in strategic planning. Any modelling, even my modelling or even common sense, would start pointing towards not putting industry and people in the floodplain. And so how would you do strategic planning here? Well, maybe you'd move your industrial area out of the flood zone. Well, it's already there. Well, okay, well, how about creating an island there now where new industrial development can go, so it's above the floodplain? We're only talking 1.5 meters above ground level in most of this area. But because it's so flat, that 1.5 meters affects nearly everyone. So the rapid flood modelling could help there. And in emergency planning, it can help. So you're not having to spend much money at all now in physical measures. You're just trying to direct people to and from areas of risk. And I took this photo because it's an obvious measure that went in after the last floods. Let's create a flood bank. But actually, this type of bank causes more problems than it solves. It'll stop 1 foot, 2 foot of water, and then that bank will breach catastrophically. So instead of having a slow water rise, you'll have a rapid inundation. And guess who lives behind it? Well, it's all the people who can least afford to be flooded. Also, it's neatly catching ponds of water where mosquitoes like to live. So there are other impacts associated with this type of ad hoc defence measure. And finally, flood warning. This is a photo from Thailand. It's one of the most effective forms of reducing impacts to people. Not necessarily the economic loss, but the social loss. I like to think of waiting for a train, actually. When you're standing on a train station and the train's late, you don't know how late it's going to be. You can't go to the toilet. You can't get a coffee. You don't know what's going on. In the UK, they introduced the sign saying your train is 4 minutes late or 10 minutes late. Just that little bit of information, knowing how late something's going to be or when something's going to come, changes your attitude to how you deal with the situation. And I think effective flood warning, whilst it can't stop some of the catastrophe, it can help people prepare for the event, particularly if that modelling's accurate and you're not issuing too many false warnings. And I think as we move forward, real-time flood warning, flood modelling, based on speeding up modelling and rapid flood modelling, will be the way we start to manage these future events. All right. Stating the obvious, really. Flood warning doesn't cost very much in red, but it's quite effective. Large-scale capital investment is very effective, but it costs a fortune. And somewhere in there, many of you guys out here have to plan where your investment's going. And I think in many instances, the basic flood warning system is all that you'll be able to afford, and therefore is a worthwhile investment to make in the modelling as well. I'm not. Yes, that's the same thing. So where are we going? Detailed modelling costs a fortune. I mean, we spent hundreds of thousands in some areas doing modelling, to the very basic modelling that I've just shown, where we can get some answers in a few days. Those costs, and in fact the time for modelling, will reduce. That's going to have direct benefits in a local scale, but I think we're also seeing the emergence of global flood risk models now, and I would hope to see them move to intelligent, real-time modelling systems that learn from river gauges, from river networks, and learn from previous events to become powerful and free tools for governments, institutions, and people to work with. So that's the positive. We then have the final step, which is apathy. Yeah, I've invested, 1 minute, I've not done bad. We've got to get over the apathy of people after this flood has happened, because floods don't happen that frequently, there's more important matters like getting food on the table, getting to work on time. And we forget about the major consequences of flooding and move to excitement, really. And I'm excited about this conference and some of the new technologies I've been hearing about sharing information, getting it across better, and linking it up with other initiatives, so making managing flood risk multifunctional. That didn't come off well, but it has to be linked to other things like freeing up planning space, getting transport better. We can't hope to do this alone. We have to link it with multimedia and energize people to do something for themselves rather than rely on an institutional response which won't have full coverage. I will end there. Thank you.
Thank you, Hamish. Thanks very much, Hamish. There is room for 2 questions. Oh, yes. Namibia.
Not about the technical issues, but did you report your findings to somebody in Namibia? Sorry, not about the technical issues, but did you report your findings to somebody in Namibia?
My 4 days for modelling finished on Thursday, so I haven't reported it yet. The intention is now to talk with hopefully you after this conference and some of the ministers about what I've experienced in Oshakati. So yeah, I haven't yet. I will do.
I won't start an internal discussion.
Okay.
No, it's okay. Well, I think, thank you.
Yeah.
I'm very happy. I think Hamish is happy to discuss it with you because it's really very hot research.
Yeah.
Thanks. All right. Thanks, Hamish.
Thank you.
I would like to invite the last speaker, Mr. Brendan Youngman from the Netherlands, from the Institute of Environmental Studies, who will say something about dynamic flooding modeling using globally available data and have an example for Africa.
Yes, thank you very much, Jaap. Thank you very much, World Bank, as well, for having me here. It's very interesting. As I said, I'll move up another level to have a situation, we have a limited budget to hire a consultant, then where will you put it? On a national scale, on a continental scale, and even on a global scale, to use globally available data to estimate flood risk. Now, 3 key messages that are all in the title here. One is that it's going to be global, so globally available data. Can we actually use it to go to risk, not just exposure, not just hazard, but to actually go to risk assessment for flooding? And then can we actually apply it to Africa? Can we apply it on a more regional, maybe national scale? And also, can we make it dynamic? Can we have dynamic exposure and hazard and risk estimates on the climate change, but also on the population change, urban growth, these kind of things? Now, we all know that we have a lot of flood events, even only in Africa. This is a picture of Cape Town and one of the townships. Last year in South Africa, we had 140 people killed in flooding. And here's a picture from Kenya and a picture from Congo. This is actually Kruger National Park in South Africa, where we see a lot of damage, but it's also positive sides. Nature benefits from flooding, and the elephants had some break from the cameras after the shutting down of the roads here. The problem only is that we know that these events happen, and we know they occur in different places, and we can respond to them, but we have no consistent model to say where are they going to be on a national scale and a continental scale, and how often will they occur and where. This is a quote by Robert Zillick, the now leaving president of the World Bank, in the last report that came out last month, the G20 report. And it points very well that indeed we do not really know where the events happen, and we need more information to say how they're gonna occur and where. I think there's 4 reasons for this: to do this on a global scale, but also on a national scale. One is just simply to identify the areas that are at risk and estimate how risky they are. Second, to estimate the expected losses from now, but also in the future going forward. What is the expected payouts needed in different places? 3, to assess the costs and benefits of adaptation measures. If you want to apply an adaptation measure, exactly like how much does it cost and how much will it benefit in that sense. And also the support the distribution of adaptation funds. So there's a lot of global adaptation funds, UN, World Bank, and also national adaptation funds. And now it's very difficult to say where should we point these adaptation funds and how much. And that's kind of how we want to look at this. Can we use global data that's available everywhere to do this on data poor areas like Africa, and also maybe on like continental scale? So some background of the studies we've been doing now, the IVM, I'm sure very few of you have heard of it. From Amsterdam. We're actually quite a significant player in Europe. We now have this project with all these partners called the Enhance project, which is 6 million euros really to do these kind of things, to look at enhancing risk assessment on international scale. So I'm not going to bore you very much with this, but just to explain later like how the damage estimates are arriving. Of course, the flood risk is a combination of the hazard, which is the where and how much is the flood, exposure, how many people and assets are in the flood located, and the vulnerability. Exposure hazard are supposed to be going up according to a lot of global reports, and the vulnerability might be going down. We've seen this in a couple of occasions, this couple of sessions. So how specifically we do this in flood risk assessment? This is the national approach used in a lot of different countries. Every country has a little slightly different approach. Where you have land use or assets that form the exposure, so we know where houses stand, what kind of houses, commercial, industrial. We have inundation depth from these detailed inundation models, and there are vulnerability functions that say for different types of land use, if you have a given water depth, what is the damage as a percentage of the total value available there. Now, of course, you can imagine if you want to scale this up to an international level, to do this in Africa and do this on a global level, that you have challenges in each of these levels. So for the land use and exposure data, there are a lot of land use data available, but of course they're more coarse and they're less detailed than the national data. Then the hazard part, there are a lot of inundation models, as we've seen some of today, and now we are presenting here also a global inundation model, which also validated and see how this compares to reality. And then vulnerability is also, of course, a very difficult thing because it differs per country, even differs per city. And is it feasible to make some assumptions that concur with reality? So just to give you some visualization of some data available here in Africa, for example, this is just a satellite picture of the continent. We have for some sources, we have land use maps, we have for now, but also a couple of years ago, even going back to 1970 from some sources, where you see where the cities are, where the green areas, where the agricultural grounds are. We have infrastructure networks, also free data available, for example, from OpenStreetMap. And then what we already have is floodplains. It's a database of floods since the year 2000, available through the Dartmouth Flood Observatory. And if you even overlay all of these, then you get simple indicators like exposed population per region in Africa. And this is something that has already been done in the Global Assessment Report, for example. You can easily look at exposed population and how that changes over time. Now, the interesting and difficult thing here is to go from these simple static exposure estimates to something that's dynamic. So can we have dynamic hazard, dynamic population, and urban, and these kind of things to see how things change over time. Now, what we have together with Deltares, who developed this model, we have the global inundation model. Currently up to 1 in 30-year floods. We calculate by using climate data, elevation data. Here you see the inundation model filling up. And we're able to calculate these 1 in 30-year floods for now, but also up to 2050 using different climate scenarios for the whole world. The resolution is 1 by 1 kilometer, and the inundation depths are about 10 centimeters. But of course, as the gentleman in front will agree that there's of course a lot of uncertainty in all of those. Now, we did some validation of this hazard model as well in Bangladesh, and this is Mozambique, where we've done some validation. This is what the satellite observations from the Dartmouth Flood Observatory give from a couple of extreme floods since the year 2000. And this is what our global flood model gives for the 1 in 30-year estimated flood. So you see the big picture. It looks like it gives a right picture, both in both streams here and also in the downstream area. And there's some difficulties. For example, here there's a wetland area that's not represented very well, and some areas are overestimated, some are underestimated. But if you test it on the global scale, then we are quite happy with the results you can get from this globally available data. So from this we did a case study on Mozambique as well, how we can go from this global hazard data to global flood risk impact. For exposure we used 3 land use types that are all available online as well. So if anyone's interested in doing an assessment like this, you can reproduce it very easily, and I'll just send you the link to any of those. We have an urban density database, which gives the urban density from 0 to 100% for all areas. A crop density base or database, also a density, and then infrastructure from OpenStreetMaps. We have the main roads and main railways in Mozambique. The hazard is this global inundation model. We run it for the 1 in 30 year for the reference scenario. And then we have vulnerability. We made assumptions about vulnerability functions. So we actually applied a European methodology in vulnerability functions, and there's more data needed to actually make more differentiation within Africa, within the world as well. So this is what it looked like with Mozambique. This is the crop density database from light green to darker green, where there's more density. We have the city areas and the infrastructures see here. And then we overlay our global flood model here for the whole of Africa to arrive to flood risk areas. So this is a map of actually with light red to dark red, the more risky areas, the most expected damages within Mozambique. Now this map, of course, you can't use it to apply like, okay, well, we're going to use these areas, have to focus on. It's more an indication to see maybe this would be an area to hire a consultant and do more research on these areas, of course. So what the damage calculations give for Mozambique if we run our damage model. This is the observed year 2000 floods. It's from a World Bank report. You see it's 1.2 billion US dollars for part of Mozambique that got flooded that year. And this is what our model estimates give for the entire of Mozambique. So you see it's higher, of course, because we model a larger area as well than was flooded here. And we have some higher estimation, probably some overestimation in urban areas and some underestimation in crop areas. So this gives some leads to how we can adapt this model for Mozambique to apply the indicators in a different way. Now what we're also working on now, it's very much work in process, is to go to population impact. So there's a lot of global database on population, not only the number of people that are living somewhere, but also poverty count, age breakdown, and the average health and development. From that we can go to, currently going to mortality risks, it's expected number of deaths, given flood depth, and also given poverty and health, and different governance indicators for different countries. Yeah, and as said, the major advantage of our method, at least what we're going to go to, is have a dynamic model to assess flood risk. So what you see here, for example, is the red area is population, and the orange area is population, the red dots here are the urban areas, and then the blue is the inundation model, which is projected from 2010 to 2050. And with this dynamic approach, you can actually assess what is the contribution of urban growth, contribution of population intensity, and of contribution of also climate change in increase in flood risk here in Mozambique, but across the globe. Finally, you can do a simplistic, on a global, on a national, regional scale, you can do simplistic adaptation measures, modeling through this model. So we have now, we make some assumptions about the standard of flood protection, and it's very easy to make new assumptions. If you say, what would be the contribution if we increase the protection standard from 1 in 10 years to 1 in 20 years, and then you can calculate the expected annual damages and see what would be the contribution of making such a step in your protection standards. Same you can do for exposure reduction. You can reduce the value of assets located in flood zones, and also the vulnerability. You can say if all of our buildings would be less vulnerable to flooding, what would be the contribution of that? And then eventually you can end up for each country with these kind of pictures where you have a baseline scenario and baseline, the current expected damages. 2 scenarios, you see the increasing over time due to socioeconomic development, climate development, and both. And if you then apply adaptation, would it, oh, the picture came out a bit funny. Then if you apply adaptation, would the expected damages be decreased, and if so, by how much? And you can make a simple cost-benefit analysis on your national scale with these global data. Finally, also want to say that this can be upscaled. So, for example, for the global assessment report, it would be, in our feeling, a very added value to make this dynamic approach part of a global assessment of flood risk and see within different countries, where are the areas that are most affected now in terms of urban area, in terms of crops, infrastructure, population, how does it change over time, and how can we change this by global development, global adaptation financing. So here's a couple of links to, we think, to stakeholder operations of this global flood risk model. First, quantifying and mapping of current and future flood risk, then linking it to adaptation planning and financing in a quantitative way, assessing the effects, the real effects of development, of poverty reduction on flood risk, application short to medium term disaster planning, and we want to contribute to global studies. Some of this information is also in the GloveRIS folder that's on your seat. So if you have any further questions, I'll be happy to answer them. Thank you very much.
Right. Thanks, Brandon. Any questions? Yeah.
I wanted to break a record of asking questions to every speaker, but I missed the last one. But this is not really related to the last presentation. I guess I want to take 1 extra minute. When I was doing my PhD 25 years ago, we were competing, you know, how many milliseconds or seconds of computing time you can save. My professor, he solved a large matrix, saved 3.5 seconds. I said, I'm much prouder than the professor. I did in 3.2 seconds. Nowadays, we don't talk about computing time. Like, how many hours or how many weeks do we use to read TORs from the World Bank? How many weeks does the bank take, how many months or years does the bank take to allocate a contract for a real-time telemetry network to a contractor? I think if you talk about real flood risk management project, flood modeling doesn't have to be done very quickly. We don't want to miss the details. I think hydraulics, the details in the ground, as you said, is done one time, not every day. When it comes to real-time flood forecasting, of course we need a speed. There are tools to do that. But I mean, this applies to the whole session. I guess we need to produce a very accurate flood information based on ground, based on data, based on science. So I think we should be very careful. It takes 3 years. A project I'm doing in India, it has taken 3 years to install telemetry. And you are asking me to do the flood model in 3 days. It's very unfair. So I think we should really think that we should go into details of flood modeling. Thank you.
Yeah, I agree on you with on some point. If you want to have a very detailed analysis and you want to know every little centimeter of your village, and you should take a lot of detail, you should take a couple of weeks to calculate your model. But especially if you want to run scenarios, if you want to look how things change, you want to do it rapidly. So even this model will take a week or so to run if you want to do it on a global scale. The model that's used in 2009 in the Global Assessment Report, the global model, took about 16,000 hours for all the basins to be computed. So there's different purposes for different things. And I think if you want to do dynamic scenario analysis, then speed does matter, I think.
Question, those flood damage curves, you showed them, that's from Netherlands.
Yeah, we now apply
I mean, how many countries in the world can say they have something like this? I mean, it's a nice message to every country. Whenever disaster, especially flood, happened, it's crucially important to go systematically record the damage. That's the only one way to have something like this. How many years Netherlands is doing these things? For how many years? I mean, how many floods, etc.?
Not too many, actually.
No, that's the interesting
Sorry.
thing.
To be very fair.
You can laugh, but I spent 6 years in Germany talking to the German government, how many years it took them to develop all these things. Yeah. And second, for novice people here, maybe the impression is if you overlay these things and you press button and GS will solve all your disaster risk problems, I mean, still be careful about this.
No, and you're very right. And I just finished a study with the European Commission where we compared different vulnerability models. In every country within Europe, even Netherlands, Germany, there's about a factor, up to a factor 20 difference between all these different models. So even there's a lot of uncertainty, and you need to be very careful with this. But so I would really urge you to do some sensitivity analysis. And that's also the nice thing if something is rapid and you can do sensitivity analysis, you can compare with observe data and see which fits for different countries.
Okay, please.
Thank you very much. It's very interesting to see hydrologists and hydraulics engineers arguing about modeling time, level of accuracy, the budget involved, and all this. What we would like to understand, I'm not an engineer, I'm a disaster manager. What I would like to understand is, can we have thresholds of what level of accuracy is needed for saving lives? That is a relief operation, or when you are in the middle of an emergency, for rehabilitation or reconstruction, or for development. And the development, you have the luxury of time. If it's development, you can do it 3 months, you can do it 6 months, no problem. But we are talking about disasters and we are talking about risks. And people are only alerted to disasters when there is some warning that there is a cyclone coming. You have 2 to 3 weeks to do some modeling and give people information that can be used for decision making. So is there any way we can have thresholds?
I would like to ask someone in the audience who spent 6 weeks in the war room in Bangkok during the flood, to say something what kind of information he would have liked to have. And that was, that was clear and present danger, right? Yes, well, day and night.
That was very exciting indeed, because you have, on the one hand, quite a bit of time. It was a very slow flood. On the other hand, every day the flood is coming nearer, and there was a lot of confusion about the information. So we're discussing a lot about models here. The first thing I would like to say is that the models, they provide a lot of information about how the system behaves. And that was the biggest problem I faced at the beginning when I stayed there. What is happening? And people didn't understand what was happening. They know the flood is coming, but how far will it go? And then we constructed, like Hamish did, in a very short time, a two-dimensional model, and started running it. Of course, at the beginning, without the dikes, without pumping stations, so the results were not completely correct. We also didn't know how to set manning values, roughness values, and so. But gradually we learned. Within a week or so, we got already a lot of grip on the quality of the model and the forecasting capability. And then it was very amazing that at a certain moment you read in the most important newspaper, if a dike breaches along the river, then within 1 day, whole of Bangkok will be flooded. I was reading this in the morning at the breakfast table, and I said to my friends, what a nonsense they write here in the newspaper. Because it takes at least a week or so, maybe 2 weeks. And that's what I got out of my simulations. It proved to be, at the end, quite predictive. By the end of, let's say, nearly a week before the flood reached the most downstream point, we were able to calculate a month ahead at the moment, and it proved to be correct at the end, based on a good digital elevation model. And this sort of information can be extremely important, even during, let's say, such a period where everyone is nervous. That has the advantage that you get all the data very quickly, of course. But I would like to, let's say, expose this as an example where models can be very useful, also the less accurate models. So I mean, it's an endless thing to talk about. So
yeah, it's okay.
Everyone is welcome to talk with me about it in the breaks and so. But I learned a lot there, but a lot of other people learned a lot as well. Yeah.
Thanks, Adrian. Any other questions? It's late. Jonathan.
I have one quick question. On what type of model do you base that 10 centimeter accuracy? If the terrain models don't have that accuracy?
Hassel, you want to answer that?
Yeah, well, is this one switched on? Yeah, okay. Well, this model where we use a sort of a step of 10 centimeters to sort of fill up the elevation model. So that doesn't mean that we really have an accuracy of 10 centimeters. We just fill the elevation model up with the 10 centimeter rate. And once we take the amount of volume of water coming from a global hydrological model that flows over land, And we fill that up in the elevation model, and we do that stepwise. That's why the 10 centimeters was mentioned.
If you have an elevation model with 10 meter contour, sorry, if you have an elevation model with 10 meters contours that are 20 kilometers apart, then yes, you can calculate 10 centimeter intervals, but they don't have any physical meaning on the terrain.
Yeah, okay. Well, it's a bit of a detailed question, so perhaps we should talk about it during the break. But we just fill it up until the volume is accounted for, and we do this with 10 centimeter steps. 1 meter would probably be too much, then you sort of are over the volume already of what you have to account for.
Oh.
I think I must make a comment here. When we talk about 10 centimeter resolution in the model results, it's normally based on LiDAR collected data. And there you have this sort of level accuracy. But still, of course, many places in the world don't have LiDAR data. So we use normally the NASA data set, which has a very inaccurate, of course, representative of the level. So you cannot use it at all for flat areas. For flat areas, you really need LiDAR data to do any sensible calculations. Now this new set of data comes up. I mean, Hessel brought it forward. I must say that 1 meter, I didn't make the remark at that time, but now is the appropriate moment. Doesn't help us still very much. I mean, for the flat areas, this is not enough. So we really have to go to LiDAR data collection in that case, if we want to have this full understanding of where the water flows and the measures we can take.
Okay, thanks. Before I want to close the meeting, I would like one announcement from the organization, and that's not a very nice announcement, because an iPhone was recently taken from a food table downstairs. So please I want to remind everybody to keep track on their belongings. I mean, you cannot leave it everywhere, yeah? Please do so. With that announcement, I would like to close the meeting and thank everybody for being here, and thank the speakers for their very nice talks. Thanks very much.